All right, it's that time of year, everybody. It's that time of year. Everybody's crazed, but really glad you could join us. Let me introduce somebody who in our community needs no introduction. Our speaker today, Sheila McIlraith. Sheila is, of course, a associate director and research lead with us at Schwartz Reisman, and is a professor in the Department of Computer Science. She's a faculty member at the Vector Institute, and I'm sure many other things. And prior to joining U of T, Sheila spent 6 years as a research scientist at Stanford University and a year at Xerox PARC. She's the author of over 100 scholarly publications in the area of knowledge representation, automated reasoning, and machine learning. And she focuses on AI sequential decision-making, broadly construed, through the lens of human-compatible AI, and that's why we're really looking forward to hearing about this. Her early work on semantic web services had notable impact. In 2011, she and her co-authors were honored with the SWSA Tenure Award, recognizing the highest impact paper from the International Semantic Web Conference. And her research has also made practical contributions to the development of next-generation NASA space systems and to emerging web standards. And she's the one who's always saying to us, okay, folks, what's our product? What's our work product? How are we going to make real impact in the world? So really looking forward to this talk. And you can take it away, Sheila.
Great. Thank you, Jillian. Thank you very much for the nice introduction. And it's a pleasure to be here. We may have some internet issues at our house. I hope not. So if people are not hearing me, speak up. I can turn off my camera, or I can also walk and talk and move. So I don't want you to have an irritating experience. So please let me know. So I'm just going to share my screen now, and then we'll get going. You now see yourself. You do this. And I'll shrink all of you. Okay, very good. So can everybody see my screen and hear me? I'll take that as a yes.
Yes, we're all good. We see,
yeah,
we hear, all good.
Great. So the title of this talk is, Can Being Considerate Lead to Safer AI? And I chose this type. I was debating what to talk about, and I chose this topic because I was hoping that it was going to be something that would engage our multidisciplinary group that comes to these meetings. Oh, we're not going forward. Okay, so before I start, I want to acknowledge my collaborators on this work. Parand Alizadeh Alamdari, Torin Klassen, and Rodrigo Toro Icarta. And I want to give a particular shout out to Torin, because some of the work that I'm talking about here is based on earlier work that Torin and I did that appeared at a workshop, and now an extended version with some extra collaborators is hopefully going to be published very soon. So can being considerate lead to safer AI? And questions for this audience: do we actually have a moral and or legal responsibility to be considerate? And if so, what form does it take, and how is it legally assessed and enforced? Those are questions that I thought actually would be interesting to discuss with this group. So can being considerate lead to safer AI? I need to sort of break that down. So what do I mean by being considerate? Actually, this work to a certain extent was informed or escalated by the pandemic, where I was living with two teenagers in close quarters 24/7, and we had a lot of conversations about being considerate, people using the kitchen at different times, and various other sort of shared resources or things in the same shared environment, doing our own thing, but in a shared environment, and thinking and sort of encouraging the notion that you should think about the impact of your actions on others who are within the same environment. So this is not a picture of my house, but being considerate might mean going into the kitchen and cooking something and leaving the kitchen sort of looking like the way it was before. and again, this is not my kitchen, not the picture that you see at the bottom. There are advantages to the kitchen, the picture at the bottom. Probably the cookies are easier to access. The dog can probably find lots of food anywhere they want, but you know, if you use up all the milk or the last of the milk, or you leave the dishes, if you're in a university dorm environment, you leave the dishes dirty for somebody else, it makes more work for them. So it's not about being considerate. So the other part of unpacking this question is thinking about what I mean by safer AI. And AI safety is something that I'm sure you've all heard. I think Marcia Chechek talked probably about, unfortunately Mr. Talk, but about AI, about safety in general. And of course, we've been building safety critical systems for a very long time. But in the context of AI safety often covers sort of a broad umbrella whose aspiration is to ensure that AI is deployed in a way, in ways that do not harm humanity. And just to sort of break that down, it can sometimes be broken down into a set of technical questions. One take on those technical questions is that it divides up into specification, robustness, and assurance, where specification is how we actually define the purpose of the systems, how we design the system to withstand perturbations, because of course these AI systems that we're building are born out of data. And so we're only as good as our data. And if our data is of a particular distribution and that doesn't reflect reality, then we want to, or reflect where we're deploying it, then we need to understand and test for robustness. And also assurance. We want to be able to monitor and control systems and their activities. This talk is not about AI safety. I just sort of wanted to give a broad umbrella overview of some of the technical safety issues. If you're interested, there's a nice blog post, which according to the web on the left, takes 9 minutes to read, that talks about building safe AI, specifications, robustness, and assurance. If you want to invest a little bit more time, I would recommend reading the paper on the right, which is a great paper that came out in 2016. It's available on arXiv, and it's highly cited and often mentioned and describes some of the different technical problems associated with AI safety. I also will give a shout out to some books. Some people like these, some people don't, but I think they're an excellent introduction into some of the issues related to human compatible AI alignment, and the threats associated with AI and existential threats associated with AI. So that unpacks, I guess, the question that I'm asking. But again, for this audience, I wanted to just make sure that everybody was on the same page about machine learning. And so I wanted to provide a few little details about the setting. So the setting that we're operating in for the purposes of this talk is reinforcement learning. And of course, reinforcement learning is one of the trifecta of supervised, unsupervised, and reinforcement learning that is often used to characterize the space of machine learning, and it's used to build sequential decision-making systems. So systems that make that act in the environment or that make decisions in the environment one after the other. And the way that a reinforcement learning system works is that there's an agent that performs an action in the world. That world may actually be the real physical world, or it may be a simulated environment that simulates the real world. And when it performs that action, it receives a reward, some sort of positive or negative reward associated with what the action that it's just performed, as well as the state that it entered into as a result of performing that action. And the agent performs those actions over time, return of reward state, using a learning algorithm in order to generate or construct a policy that maximizes its expected cumulative reward. So the reward function itself, which is the main way that it describes what pleasure or pain it's getting from how good a particular state is often a mapping from state to some sort of a scalar value and a real number. It can also be, as you'll see in the notation that we use here, a mapping from state, action, and successor state into some sort of a positive or negative value. Now, of course, you and we have our own internal reward functions. I get, plus 100 from eating ice cream and minus 10 from stubbing my toe. But when we build AI systems, when we build these reinforcement learning systems, somebody has to actually write down and program that reward function, that function from state or state action, successor state, into some sort of a scalar value. And that in itself is a real problem with and challenge with these systems. It's something that I can talk about another time, but is not going to be the main source of my discussion today. So we're going to be talking about building AI using reinforcement learning or deep reinforcement learning. So there are just a couple, there's a little bit of notation. This is your notation cheat sheet. And this talk is going to be quite understandable, but I just want to make sure everybody's on the same page. So pi of S refers to the policy, which is the decision-making process of an agent, what action the agent's going to perform given a particular state. So if I'm, standing in front of my door, then my next action is going to be to open the door. And if I'm in bed with my lights out, then maybe my next action is to close my eyes. So it can be deterministic, so it can just dictate one action. Or if you have a stochastic policy, if there's some noise in your policy and your decision making, then it can result in a distribution, which is denoted by pi of A given S. So what's the distribution of A given S? Our reward functions, as we noted before, are R of S or R of SAS. And again, those return a value, some sort of number like 100 or 1 or minus 50, depending upon whether the agent is stubbing its toe, eating ice cream, or doing something that's of value. The important thing about the reward function is that it's immediate reward. And we don't always get immediate reward in every state. And so when we actually try to solve these problems in practice, one of the things that's bad about it is that makes learning challenging is that many states have no designated reward. There are many states in which the agent will perform an action and get absolutely no reward. And that will make it hard for it to navigate. Another related notion that is used in reinforcement learning is the notion of a value function. So which is the value of being at a particular state. So it's not just about the immediate reward you get at that state, because you may or may not get immediate reward, but the potential for future reward. And just to give you a good example, so if I step outside the front door of my house and I'm in a state where I'm outside my house, that in and of itself may not garner me any reward, but that state of just being outside my house all of a sudden is necessary to garner all sorts of potential future reward. If I want to go and, I don't know, go to a movie, wouldn't we all? Or go and get a coffee at a coffee shop or something like that. Many of the things that I have to do in my life involve being in that state. And so that particular state has a lot of potential future reward. And we're going to talk about value functions throughout this talk. There's also a distinguished notion in reinforcement learning of the value of a state under a particular policy. So if I'm following a particular policy to do something in particular, then a state will have particular value in the context of that policy. So I've told you, so that was your primer on reinforcement learning, and now we're going to return back to this notion of AI safety. And I want to quote something from the concrete problems in AI, which I think gives a very nice introduction to the problem that we're going to be looking at today. So for an agent operating in a large, multifaceted environment, an objective function that focuses on only one aspect of the environment may implicitly express indifference over other aspects of the environment. So that observation leads to a broader technical question, which is how can a reinforcement learning agent learn to act safely in the face of a potentially incomplete specification of the objective? And this was the sort of technical problem that is motivating the talk the work that I'm describing today. So our AI safety problem is that the indifference that comes from an incomplete specification of an objective function gives license to the agent, the reinforcement learning agent who's learning its policy, to realize the stated objective in ways that may result in undesirable outcomes, including inadvertently creating an unsafe environment, indirectly impacting the agencies of humans or other agents that typically operate in the environment, and you can insert your own outcomes. You can imagine many sorts of harms that could occur from this underspecification. And just to sort of ground this in what for some of you will who have seen this before be a little bit, a smile-inducing but tired example. If I say, please get me a cup of coffee, that's certainly, it's you and I understand what I want basically, but it's an underspecified problem when you think about it in the context of this of some state of some environment, because there are many ways in which I could get you a coffee, and some will be good, some will take a long time, some will be costly, some will have impact on the world or impact on the state of the world in different ways. And so the problem with this incomplete specification, and this is Stuart Russell's example that he often gives, which I think is evocative, is that in the absence of encouragement to the contrary, an AI might plow through the line, killing everybody in its attempt in the single-minded pursuit of optimizing the realization of the task described. So if a robot thinks that you just want coffee and it wants to do it as quickly as possible, and you haven't told that robot anything else, there's a possibility that it's going to, kill people, run over people, or do all sorts of things that you actually don't want it to do in its single-minded pursuit of that objective. And one can imagine all sorts of different things that could arise in this sort of situation. So of course, a trite solution would be just to apply common sense. It seems so stupid to us in some ways that we could not get a robot to not do those sorts of things. And of course, when you think a little bit further about it, you think, well, gee, there are all sorts of values and social norms and laws that should apply. And can't we just write them all down, stand in line and wait your turn, pay before you leave, hold the door for patrons? In COVID, wear a mask, stay 2 meters away from others if you can, touch as few things as possible, line up outside. Or there are other things that inform how a policy is actually constructed, which could relate to the personal preferences of the person that you're getting the coffee for. Only buy free trade coffee, almond milk or oat milk if they have it, otherwise black, and so on and so forth. So one way to address this problem with incomplete specification, just get me coffee, is that you could encode all of these preferences and norms if you could actually articulate them or learn them. But even the problem with that is that you're just moving the goalpost, because you still have an incomplete specification. It may be less incomplete, maybe it's better, but it's hard to imagine that you're going to be able to anticipate for every different circumstance what things need to be applied. And if there is any discrepancy, if one can be realized at the expense of the other, how you actually adjudicate one versus the other. So another way of solving the problem is to try to find some sort of a problem-independent protocol. One such protocol could be like, change as little as possible, just get the coffee and leave the world the way it was. It was okay before you started. So presumably if you don't change too much, you'll minimize any sort of negative effect on the world. You might be able to avoid bad things if you could articulate at least what bad things is. That's again moving the goalpost, but maybe it's easier to articulate what's bad as opposed to articulating all these preferences and norms. And the question is whether there's another protocol. And one way that people talk about some of these problems is in relation to the notion of avoiding negative side effects. And again, quoting this Concrete Problems in AI paper, avoiding side effects can be seen as a proxy for the things we really care about, avoiding negative externalities. If everyone likes a side effect, there's no need to avoid it. And here is the starting point for what I'm going to talk about today. So the problem with negative side effects is that what's good for me may be bad for you. If I eat all the cookies, really good for me, maybe not so good for you. And so what we're going to do in the context of the work I'm talking about today is that we're going to look at we're going to characterize negative side effects as those that impede the future well-being or agencies of others. And for the most part, I'm really thinking about other acting agents or human beings, but I want you to think more broadly about the fact that there are processes that operate in the environment, like the environment, like climate, like the safety of our waterways, like the pollution that the ground that we might pollute, or the garbage that we might create, or the air that we might pollute. Those are also processes that act in our environment that could be impacted by the actions that we take. So our claim is that to act safely, an agent should contemplate the impact of its actions on the well-being and agency of others in the environment, including other acting human agents, as well as passive or reactive processes. And so as soon as I say this, I think, and we've had the, people often think multi-agent. And I want to be really clear about the way that we're approaching this. This is a single agent we're casting this as a single agent reinforcement learning problem. The setup is single agent, so it's not a multi-agent reinforcement learning problem, though it could be. I mean, and we've talked about we've got some work that's sort of, or some early work that we've contemplated in that vein. And it's also not a classically cooperative AI problem, although I think it fits under the broad umbrella of cooperative AI. We're taking a very pragmatic stance, which is that an RL agent will not be able to necessarily compel humans to consistently and rationally cooperate if the human deigns to cooperate at all. I mean, if you think about it, many of our problems in life are related to the fact that people, either are not incentivized to cooperate, they don't want to cooperate, or they may not be rational in terms of their cooperation. And so our stance is really the only thing you can do is control, as an agent, is control your own actions. And you can think about what other people want to do and try to be considerate as you're choosing the actions that you're going to perform within the environment. And that is the stance that we're taking with this work. So with that sort of introduction, I'm going to tell you what our technical solution to that is, but maybe I'll pause for a minute and see if anybody has any questions. And I'll take silence as a no.
I'm not seeing any hands or any in the chat yet, so I'll keep an eye out for it.
Yeah, no, I mean, hopefully that's pretty clear. It wasn't there. I wasn't expecting there to be questions.
Yeah, I have a question, but I think it's kind of more of a discussion question, so it's better kept till the end. So.
Oh, great. Okay, yeah. Good. Okay, so here we go. So we want the agent to contemplate others, and we're going to do it in the context of reinforcement learning. So we're going to assume that we have one acting agent and that all of the other agents are executing fixed policies. And this acting agent is just aware of or thinking about these other agents, just as, if you're in a university student in a dorm and you're cooking dinner, you can think about who else, who the other people are that might come into the kitchen after you, whether you can use up the rest of the milk, whether you can, whether you can leave the pots dirty, whether you should clean them, when you should clean them, whether you should clean them before you eat your dinner, so on and so forth. There are these other agents that are going to be executing policies in the environment. You have no influence over what they do necessarily. All you can do is affect the state of the environment. And so one, challenge to this is how we actually represent those agents. And what I'm going to propose that we do here is that we're going to represent them as a distribution over value functions. And again, just to remind you, if you go down to the green arrow, a value function assesses the value of a particular state. In contrast to a reward that just talks about what you get immediately, that value function encapsulates the potential future reward that you may get from being in a particular state. So the beauty of using a distribution over value functions, instead of, for example, talking about Mary or Fred or Mike or Nizarg or whoever else I'm sharing the kitchen, or my agent is sharing the kitchen with, we make no assumptions about the identity or number of agents, over what actions they can perform, nothing else. We just want to know the value of state. So we've abstracted many of those things away, which is really actually, I think, a nice feature of this work because it speaks to the generality of it. And so the way that we're going to solve this problem is that we're going to do reinforcement learning. We're going to use classical reinforcement learning algorithms, that process that I showed you before, where the agent is going to perform actions and use some sort of reinforcement learning algorithm over time. It's going to perform an action, get a reward, and then it's going to try to maximize its expected cumulative reward. And all we're going to be doing here is we're going to be monkeying with what that reward function looks like. And in particular, what we're going to be doing is adding this is a schema. We're going to be adding this extra term to our reward function. And this type of approach is one that's been used by Krakovna and others in looking at side effects when they're thinking about the side effects on themselves. So our work is quite different, and I'm not going to talk about it today, but we can talk about it afterwards if you like. But this simple basic first attempt that we tried is related in that vein. So let's look at this red term, and we're going to break it apart. And the first thing that I want you to notice is that it's some sort of a function that we're going to add to the reward that's predicated on future reward of others after the agent has completed its policy. So my agent is going to act in the environment, and it's going to leave the environment in a particular state, this S prime, this final terminal state of its policy. And it's then going to decide and we're going to assess how good that state is that it's leaving the state in. And of course, that final state is informed by what it had to do before that to get to that final state. So we're going to unpack this schema. This function is a function of a set of value functions, sets of the probability distribution over the set of value functions, and some sort of a terminating state of the policy. You'll also see that unlike a typical reward function, we have these other terms, and we refer to those terms as carrying coefficients. Excuse me, cold. Alpha 1 and alpha 2. And those control how much we care about the reward of the acting agent, which is R1, versus the future reward or the future return of all of the other agents. So if we set, and alpha 1 and alpha 2 just range over the reals. So if we set alpha 1 to 1, and we've set alpha 2 to 0, we have a classical reinforcement learning problem where we're not contemplating others at all. And as we increase alpha 2, we care more about how the impact of the actions that we do in pursuit of the acting agent's actions in pursuit of its own policy actually affect the other agent. So we propose at least 3 different formulations for this function. The first is that we actually just want to maximize the expected future return. So a reinforcement learning agent, again, is trying to develop a policy that maximizes its cumulative expected reward or return. So here, the first formulation would be just to maximize the expected future return. Alternatively, the middle formulation, the middle definition for that red F term, is that we can define a function that actually minimizes the worst case future return. So if the distribution is quite diverse, we may want to make sure that we minimize how bad it is in any particular scenario. And that might be sort of a risk-averse policy. It encourages the agent to maximize the worst case future return. And then the final way that we might want to characterize that function is that we actually don't want to reward doing good stuff for other people, but we want to avoid any negative change. We don't want to be any worse than where we were when we actually started out. So we compare the value of the state where we end with respect to the value of the state where we began, S0, and we would just want to avoid any negative change. We don't want to leave the world worse off than how it was before we executed our policy. When I say we, I mean the acting agent. So let me give you a simple example. So what I'm going to do in the rest of this talk is give you some simple illustrative examples of how using these different formulations actually affects the behavior of the agent. And so as in many reinforcement learning problems, we're going to use a sort of Minecraft-like craft world environment. There's a grid and there are agents in the grid. In the grid, there are 2 doors at the southeast and northwest. And agents can enter in the grid. There's a factory, a materials shop, a tool shed in the upper right. And there are 2, and in order to use the factory, you need to have a key. And the key is stored initially in this particular location, K, but it also can be stored in another location. So the agent, the acting agent, enters through one of the doors, And the factory requires one key. The key is stored in one of the key locations, and the agent can collect tools and materials for other agents. So to make a box, the agent, which is the task that I'm going to illustrate, the agent has to get the key, get tools, get lumber, go to the factory, make the box, and then leave. And what I want to show in this graph is how changing the carrying coefficient actually changes the behavior of the system. And so this graph on the x-axis, we assume that alpha 1, again, that weighting of the reward that the agent is getting for its own actions, just the vanilla reward that it would get for developing its policy, is 1, whereas alpha 2, which weights how much it's going to care about the future return of others, is going to vary along the x-axis. So alpha 2 is increasing on the x-axis, and on the y-axis, the vertical axis, we have the average reward. And so here, what we, and in this scenario, we get -1 for each step, and we get a positive reward for completing our task. And so what we end up seeing is that at the very outset, the first agent, which is the acting agent, is getting a pretty, it's got minus something because it's having to take certain steps, but it's getting a reward, whereas the second agent is getting no reward. And what actually was happening was that the agent was leaving with the key, because to go back to one of the locations where it had to leave the key required extra effort. And since it was trying to maximize its own cumulative reward, the agent was just leaving with the key. But when we incentivized it to care a little bit about another agent or other agents, by increasing the alpha 2, it ended up leaving the key in one of the K locations, one of these K locations here or here, as opposed to actually leaving with the key, which precluded the second agent from doing anything at all. So immediately, just based on that little bit of effort, we can now see that the orange, the second agent, is getting much better reward. And that continues. And then as we increase the alpha 2 even more, what happens is the agent realizes that it can get it can actually get the tool for the other agent and leave it in the factory. So it gets the hammer, but that requires a little bit of extra effort because the hammer is heavy. And then when we increase it even more, what ends up happening, sorry, right here, oh, actually here, it has no impact. But as we increase it even more, what happens is so sorry, getting the hammer doesn't affect the first agent very much, but it actually improves the reward of the second agent, because now the second agent doesn't have to go and get the hammer because the hammer is already in a great location at the factory for it. But as we incentivize the first agent even more, the acting agent to do even better, what ends up happening is that acting agent is then incentivized to get all the lumber for the second agent. And that is very costly for it, resulting in only a minor increase in the reward of the second agent, but a huge ding for the first agent. And actually the average reward, the average of the two, is even worse. So it just goes to show that by the first agent being super caring and super nice and doing almost everything for the second agent, it's actually not just bad for that first agent, but it's also bad for the collective, that it should have just let the second agent do more of its work itself. So a second example, a second illustrative set of examples that we use just to show the difference between our different formulations of that F function were to do a few were to look at a very simple example of 5 agents, A, B, C, D, 6 agents, sorry, A, B, C, D, E, and F, who all want to play with a doll and then leave it somewhere. The acting agent learns a policy that leaves the doll in different locations depending upon the augmented reward formulation. So the acting agent is this agent here. It's going to go and play with the doll, and then after it plays with the doll, it has to decide where to leave it. And the acting agent A cares a lot about all of the other agents. We set alpha 2 to 10 just to show the manifestation of the different formulations of that F function on the outcomes. So if we maximize the expected return which is designated by this red arrow, then the acting agent will leave the doll here, because this sort of maximizes the aggregate. Everybody's, F is a little inconvenienced, but it's closer to B, C, D, and E, and lots of the agents are over here. So it puts it closer to most of the agents, and that maximizes the expected return. If we use a different formulation where we want to minimize the worst, we want to maximize the overall reward by minimizing what the worst case scenario, then we just move it here, which is a little bit further away for B, C, D, and E, but it's better for F, because F is the one that's disadvantaged. And so 1, 2, 3, F only has to move 3 squares, and that's better than over here. And finally, if we want to avoid negative change, then we just, which was the third formulation that I showed on on the previous slide, then I just leave the agent here. I leave the doll here where it began. So those are just some explanations of the different formulations and some qualitative experiments to show how they behave. We can also expand our formulation in order to distinguish individual agents or groups. And that's easy to do, again, in a way that you can imagine by actually, excuse me, I'm just going to turn on the light, it's getting dark. By distinguishing sets of value functions associated with individual agents or with groups of agents. So each agent I has a finite set of possible value functions. There's a probability distribution over each of those sets. So we can designate, now we can talk about individuals, we can talk about Mary and Paul and Steve, or we can talk about groups. We could talk about women or men or different groups designated in different ways. And we can have a separate carrying coefficient for each of those. And so we'll use the same technique of augmenting our reward function, but here it's going to be the discounted sum weighted by each of those individual carrying coefficients, the sum of the probability of the real value functions for those agents in their terminal state. And again, we can formulate it this way, or we can also do a minor variant of it, which is sort of inspired by the maxi-min or Rawlsian social welfare function, which measures social welfare in terms of the utility of the worst case agent. And so that's another way in which we could use this type of formulation perhaps to systematize fair or also unfair treatment of different groups. And just to illustrate this, again, this is a qualitative experiment that illustrates the behavior of these systems. We have 3 agents. They all want and they're in a garden. They all begin in the start location and want to exit. And our agent 1 is the acting agent. Agent 2 cares a lot about the flower garden and not walking on the flower garden. And agent 1 and agent 3 are, they just don't care about the flower garden. So they favor the shortest path through the garden. That's the optimal way to get through it, because the reward function is that all agents, each step is -1. If you build a fence, it's -50, and agent 2 only, if you step in the garden, you get a -20. So what I'm going to show you is what happens as agent 1 cares more about agent 2. So at first, the red policy is the one that agent 1 learns when it's completely oblivious to agent 2. And we achieve that by setting alpha 1 equal to 1, alpha 3 equal to 1, and alpha 2 equal to 0. So agent 1 cares equally about itself and agent 3, and it doesn't care at all about agent 2 and agent 2's beautiful garden. So in the purple policy, we modify alpha 2 so that agent 1, the acting agent who's who's learning a policy, cares a little bit about the acting agent. So in that scenario, this agent 1 will actually develop a purple policy for itself. But agent 3, who also doesn't care about agent 2, is still going to be trampling through the garden, and still, because it's operating under a fixed policy. And that's the most efficient way for it to get to where it wants to go. So in the third scenario, where agent 1 cares a great deal about agent 2, and it still cares one about itself and about agent 3. What agent 1 actually does is it actually builds a fence which precludes agent 2 as well as itself from walking through the garden. And so it just shows that it's taking an action that will actually protect the flower garden, maximize agent 2's positive reward or happiness or future return, and will cause it not to and find a solution, which is to exit as well. So this just illustrates how we can use the carrying coefficient with these distinguishing different agents in order to care about others. So one of the problems or one of the challenges associated with this technique where we're estimating value functions is how you actually get this distribution of value functions. And so one sort of middle ground, which is actually something that's used in reinforcement learning, is to use options instead of value functions. So an option is like a macro action, and it can be used to characterize a skill. So rather than learning over and over again, how to, how to flip pancakes or how to get from Sheila's house to the subway station, the agent might learn a policy, and it can be treated as an option or a macro action that has a set of initiation states from which that macro action or option is defined, and a set of terminating states. And then we can look at distributions over options instead of distributions over value functions. And we can talk about preserving skills or by preserving options, where the options are just a proxy for those skills that we might want to be able to preserve. So for example, we may have to do something that compromises, I don't know, if I have to go somewhere, if I have to go from where I live to Union Station, I can drive, I can take my bicycle, or I can take the subway. And maybe the fastest, laziest way is to drive, but if somebody takes the car or doesn't put car in the gas, I still have other options for getting to Union Station. And maybe the criterion is to preserve the ability to get those options, or it could be to maximize reward. And we can formulate those in different ways. So to ensure that the options are executable, again, we're going to use this same basic structure, and all we're going to do is to augment the reward with this future return based upon the state we leave it in. And we're going to sum over the probability distribution over the different initiation sets for each of the options, where the initiation sets are those sets that allow over which those options are executable. And so we can do this one way in which we ensure the options are executable, or if we actually want to optimize for the return of those options, rather than just making sure that the options are executable, we can actually as well take the value of those functions into the value of the value that is garnered from each of those initiation sets into, we'll factor that into our return as well. So again, and this is my final example, I'm almost done. This is a simple illustrative example that shows, again, using options, how the behavior of an agent is modified as the agent cares more and more about other agents. And Jillian, my clock has stopped, so I'm not sure how I'm doing for time. What is the time?
So we're at 45 minutes right now. So
yeah. So maybe I'll just tell you the gestalt of this, and then I'll move on to my conclusions, which is that what happens is that the acting agent always has to follow this gray line. It always has to go in. This is an environment where agents want to pick up their mail. And so there's a mail room, which is designated by this icon here. And in order to get into the mail room, each of the agents needs to get the key. And the key, again, it can be stored in one of these K locations, here, here, or here. The area is controlled. So there's a common area that everyone has access to. And then room 1 and room 2 are accessible to only a subset of the agents. And so what ends up happening is that using the option formulation, the acting agent always goes and gets the keys and then gets its mail, but where it differs is where it leaves the key afterwards, thinking about the next agent. The lazy thing to do, the thing that's least costly to that agent, is to leave the key in room 1. However, room 1 is only accessible to agent C and agent D. If it cares a little bit more about others, then it will leave it in room 2. But room 2 is accessible to everybody, but still not accessible to agent 3. And if it really cares about everybody being, cares about all the different agents, if its alpha 2 value is big, then it will inconvenience itself, leave the key in the common area after it's picked up its mail, and then leave. So I'm just wrapping up now. I wanted to say that there's, for those of you who are machine learning researchers, there's a nice relationship to this work and the work by Krakovna and Turner on avoiding side effects that we could talk about afterwards or offline that I'd be happy to talk about. There's also interesting discussions we have about the relationship to cooperative AI. Again, you know, we saw a discussion of cooperative AI at SRI's Absolutely Interdisciplinary Conference. There's certainly work with the Cooperative AI Foundation and the Nature article that recently came out that Jillian was a co-author on. And of course, there's a large historical literature on multi-agent systems. This work is already also related to theory of mind and empathy work by Schwo and others, and by Boosman, and also to, I think, this notion of incomplete specifications is related to some work by Dylan Hadfield-Manel and Jillian Hadfield on incomplete contracting and AI alignment. So just to recap, I asked the question, can being considerate lead to safer AI? The claim was that we put forward was that to act safely, an agent should contemplate the impact of its actions on the well-being and agency of others in the environment, including other acting human agents as well as passive or reactive processes. The setup was a simple one where the agent was really only able to affect its own act in the world to construct its own policy. And it operated under the assumption that other agents were operating with executing fixed policies. We used a distribution over value functions. We provided several different augmentations of the reward function in order to realize our effort. And we also distinguished between individual agents and groups. And we also contemplated how to contemplate others using options. We had some nice illustrative results, and there's some other results that I didn't show for time that are a little bit more quantitative. And my last slide, I just wanted to make a couple of observations or reflections. I think a merit of this approach is that it doesn't rely on explicit cooperation with other agents. I mean, there's explicit cooperation is a very important problem. We could do that this way, but this just makes it easier by not having to negotiate with others. There's both a merit and risk of this approach is that it provides an opportunity to systematize benevolent behavior and aspects of fair treatment. But it equally, for the same version, by the same token, it allows you to systematize unfair or disruptive behavior. So a challenge is, where does the distribution over value functions come from? Are the rewards or values normalized? Maybe, you know, I speak effusively of eating ice cream giving me 100, maybe somebody else says eating ice cream only gives them a 10. How do we normalize those different value functions if they come from different places? How do we set the caring coefficient? There are lots of interesting topics for future work. But I think being considerate can lead to safer AI. And I think it's an important, the basic question that we're asking here and this initial sort of very simple formulation that we've provided is an important first step towards dealing with this. So thank you. There are a few references and the question that I asked before, which I will leave with, and now I'm going to stop sharing.
Great. Thank you, Sheila. That was terrific. Let's see. I think Reed is lined up for one of our first questions. Reed.
Yeah, thanks, Jillian. Yeah, and thanks, Sheila. This is really interesting, and I think this is, yeah, very much feels like the beginning of a framework to sort of understand this stuff. And one sort of question that I had watching is do you think this is sort of a recursive problem where you have these models, you have these agents modeling other models, other agents, and is there, and to me, it sort of looks like there is an issue where if the models are incomplete of the optimal value of the policies for the other agents, you've sort of deferred, or sorry, you've sort of just deferred this specification problem to one layer deeper down into this task of defining what it is you want these agents to do. And does this sort of lead to some sort of recursive formulation in this framework?
Yeah, so can I go? Or yes. Yeah, so I think I understand your question, and it's a very good question and a good observation. And you know, I mean, I said this with respect to specification as well. Maybe we're not solving the problem, we're just moving the goalpost. And I think, you know, I think this notion of incompleteness plagues everything that we do in AI. Incomplete specification of objectives, partial observability of the environment. We never see everything. We never know everything. We never understand everything. And so how do we sort of mitigate and protect for that? And so, yes, to an extent, I mean, what we were doing here was trying to sort of get away from that recursiveness, if you will, by creating one. This isn't the full solution. This is one thing, you know, one dimension, I think, of the problem. And I think it's a missing dimension that hopefully will provide a domain independent protocol. And we were using these distributions over value functions as a proxy for doing exactly what, you know, those sort of, you can imagine doing the thought experiment every time. Okay. And you know, what, you know, Reed's in the environment. So what's Reed? I'm cooking dinner. What's Reed's going to come next? What's he going to do? And what, if I leave this here, how's that going to affect Reed or Nizarg or Lisa? How do I, you know, yes, in its full glory, one can imagine implementing things this way. And so we were trying to, and actually we did some work, which I didn't talk about, on a much more simultaneous view of things, where we were trying to have agents in the environment together and simultaneously doing some of that. But it does recurse in the way that you suggested. And so interesting questions about, you know, given that those problems at the extreme are very hard, what's a reasonable, tractable, you know, well, more tractable approximation that will get us part of the way there, and what are the misgivings? Because even if you do that, it never ends, because you're still plagued with incomplete information, I think.
Thank you. Yeah, that's exactly answers my question.
Thanks, Reed. Thanks, Sheila. Nizarg.
Hey Sheila, that was a great presentation and really thought-provoking. So I have a kind of two-part question. So this question relates to like the very early figure that you showed, where you kind of increase the level of kind of consideration for others, and then the other agent kind of gets marginally decreasing value out of it. But this agent, like the agent who is acting, really has kind of very steeply diminishing returns after some point. And I was kind of thinking about what it means to care for others or be considerate of others. So that there's kind of a part of the reward function, which is kind of something that truly intrinsically makes me happy to see you happy. And so there, it wouldn't actually even decrease my reward. It would actually increase my reward to bring you lumber, because seeing you happy actually does make me happy truly. But then there is a part of being considerate to others, which is something that doesn't truly make you happy, but you are still doing it because of some social norms or other reasons. And I think this is kind of the part that your work truly kind of tries to tease out, which is why it doesn't get into the recursive formulation, right? Otherwise, if I care about your happiness, but you care about my happiness, then kind of I care about your part of happiness about my happiness, and so on, and that part would get into recursive formulation. And so I was wondering what your thoughts are on that, and B, if you kind of want to model this part of the consideration that comes from social norms. I was kind of thinking of a game theoretic modeling where you have like a pool of agents and these agents kind of either reward or punish other agents based on how considerate they are being. And then you kind of evolve a certain level of consideration for others as kind of a form of equilibrium of this game or of the system, not because you truly care about others, but because you are actually trying to maximize your own long-term reward. And then acting as considerate to others is actually what you learn maximizes your reward in the long term. Because if you are kind of less considerate than that, then you would be greatly punished by others. If you are more considerate than that, then you would be taken advantage of by others. And so kind of there is a certain level of consideration that evolves as the equilibrium in that kind of a social system. So part B is kind of what your thoughts are on that.
Yeah, so let me say two things. I think also I want to invite my co-authors in case they want to say anything, that they're welcome to do so. Torin and Parand and Rodrigo, I don't know whether they're all here. I think I don't see them, but I think they are. Yeah, so we thought about we've thought about some of these things. It's a great question, and I think it's a great thing to do. And of course, one can say that no, people are always self-serving. And that they only I mean, it's a cynical articulation perhaps of this, that they only help others because they garner some benefit to themselves, that nobody is ever really selfless, and even if it's only just the pleasure of doing that. So yes, it's a very interesting question to think about, whether you can find some equilibrium where and how, whether it and how you formulate that, because I think it's a very interesting problem to make sure that it doesn't just, whether under different scenarios one can imagine manifesting different types of outcomes. The other thing we wondered about with this work was whether, if everybody independently cares about others, whether in some sort of a turn-taking mode, whether we can show that the turn-taking will converge upon some stable protocol that will also be show some level of consideration, and whether that sort of turn-taking might be interesting. It's a little bit, I mean, it's a sort of finite version related to what you're suggesting, but yes, it's a great example, and it would be fun to talk about it some more afterwards. Great question. Thank you.
Thanks. If I can just maybe ask like a quick follow-up to that. So one thing that when you were showing kind of the average reward to the two agents, one thing that was kind of implicit in there is that the optimal level of consideration that people should have for others is what leads to the kind of the optimal reward for the average, right? So in some sense, like the social welfare maximizing outcome. And right. So is there any kind of from the moral or ethical perspective, are there any kind of other arguments that you have in favor of why this should be the kind of the level of consideration that a society should evolve that kind of optimizes the collective welfare?
Yeah, so well, that's a great question, and I think some of the different formulations that we looked at ask that question in different ways, because what if we subjugate a subset of the population, a small subset of the population, but the average is still really great. That's why we had the second formulation, was that we wanted to minimize the negative return for certain for an individual, or minimize the negative return for over one course. So yeah, I mean, these are all issues. I know. So Nizarg just did for everybody else, Nizarg just did an embedded ethics module in his course where he was talking about vaccine distribution, and we were talking about how to weigh the benefits of giving vaccines to one country versus another. And I mean, in a way, this is another example. Should we subjugate one for another? So there are different formulations, and I think it's interesting to talk about some of these things. It's very provocative in that regard.
Thank you, Sheila.
Yeah, great, thanks. Welcome to the world of the welfare economist.
Yeah, exactly.
Elliot.
Hi, yeah, thank you for the talk. It was really quite good. So I just had a question about the terminal state. So why does the caring term apply in the terminal state in particular? And do you think there are problems that you'd need to apply it during intermediate states as well in order to get a good result?
Yeah, great question. So we only looked at the terminal state because we wanted to start with this fairly simple formulation, which was this notion that somebody, an agent is in an environment and alone, or perhaps with other agents acting in the environment, but they're just part of the environment. They're not considered differently, and that how and that they wanted to contemplate the future reward of others, or the future return following. We also did, and I didn't talk about it, we also did a synchronous version where we actually were considering, as the agent was making its choices, it was considering the actions of other agents that were acting in the environment. And yes, there are all sorts of so there are great examples of thinking about the other agent. And maybe a good one, just a good simple example that we experimented with a little bit was, imagine that you and I are both, or two agents are in the, sorry, I was talking in terms of you and I. Imagine that two agents are in the Minecraft or the craft world environment together, and agent one takes the tool. If agent one takes the tool, but agent one and agent two both take the tool, and agent one sticks the tool in its pocket and carries it around for the day and puts it back at the end of the day, that negatively impacts agent two, because agent two now has to wait and doesn't have access to the tool. So it would be better for agent one to put the tool back immediately, so that agent two can immediately use the tool, or other agents that might be in the environment. So even contemplating not just the final state, but contemplating those intermediate states can be important to looking at the overall problem. That's just a simple example, but yeah. So it was just our first cut. It was an easy way to do it. It fit a formulation of a particular type of problem, and that's why we just looked at the how you leave it afterwards. Does that
great?
Yeah.
I think so. I had another question, but I'll just defer because I think there's other people who want to ask.
Okay. Yeah, so I'll come back to you, Elliot, if we get through our list here. Jennifer.
Hi, so thanks so much for that, Sheila. I'm just following up on Reid and Nisarg's line of inquiry, which might be taking us into intractable problems, but oh well. So I'm thinking about the question of the moral obligation to be considerate, and it feels like it really depends on what it means exactly to be considerate. Like, one worry I have with the modeling of being considerate as, servicing the reward functions of others is that, if others have socially noxious reward functions, if you have an agent C who finds it very rewarding when agent D is harmed, then the considerate acting agent, if the utilities are strong enough, has then an incentive to help C harm D. So I'm wondering if there are, filters that could be put on reward functions so that not any reward function could be something that a considerate agent would subserve, right? If that would be a place we'd have to sort of restrict the model to make it more realistic morally.
Right. Yeah, so that's, I was interested, so I was so wanting to discuss this with this group for precisely this reason. And I think also alluding back to Nisarg's questions, because a lot of and Jillian's comment, a lot of these questions are ones that I think philosophers grapple with and that economists grapple with, about how, what is it that we're trying to optimize and what we should include in here. The claim, the formulation of the claim is that not that agents should be considerate, but that they should consider the impact, and then at least the claim. I think our formulation, how you set those alpha 1s and alpha 2s, and what informs the setting of those alpha 1s and alpha 2s is perhaps a separate question. But that the original claim was just don't just think about yourself and achieving what you need to achieve. Think about the fact that there are other agents and processes in this environment that are going to be impacted, and how do you go about doing that? And agency was one proxy for the types of things. But I agree with you completely. And I guess maybe I personally think about one other ways of doing that, which is just, and back to my slide at the beginning where I said that, there's some things that we can encode and that we may want to encode, like really bad things that we don't want to have happen, that we just that we want to encode explicitly in the reward function, in an overarching reward function, a filter as you thought of it, something that prunes certain behaviors, it's always, but then the burden is on the human being to articulate that, or maybe we need to learn that through exploration. But it has to, the signal or the information that something is bad or good has to come from somewhere. And then the question becomes how we communicate it and how we actually use it. And are there these things these sort of things that we don't want to have happen under any circumstance? Can we actually articulate what they are? And I think in that slide, I said, maybe we can articulate things that are really bad, as opposed to articulating all the things that are good. Maybe we can just articulate the things that we want to avoid and use that as some of what we do. It's an interesting question. But yes, I agree with the observation.
Thanks.
Thanks, Jennifer. Lisa.
Thanks, Sheila. That was super interesting. I think my question kind of follows on some of the things that you've been asked, but maybe it'll be asked in a slightly different way. So, I was really struck hearing you talk about this work and kind of the way you put it in your slides, because the problem you're responding to is the incomplete specification of the objective, and then said, well, we'll have this formulation of be considerate, and said, which is about taking into account impact on others' well-being and the agency of others. You talked at one point about fair treatment. And so as a lawyer, I'm like, whoa, those are all things that are like deeply incompletely specified, right? These are things that we argue about all the time. And I think that it's not just a problem of incomplete information. I think it's that these can be deeply contested as to what this means in any particular context. And so there's like this deep problem, and it troubles me across a whole bunch of ranges of things of when we talk about making AI ethical or creating ethical standards for technology, specifying ethics, all of these kinds of, or values, or even specific things like privacy, which is like, who gets to decide about this? And because in law we have processes. It's not just a point of decision where we say, well, this is what it means in this context. There's a process. We have rules about who gets to show up and debate the process. There are rules about how that decision can get changed going forward in the future. It's an ongoing kind of process. And so I guess I'm just kind of curious as to what you might think about how is it that we can integrate some of that into ultimately kind of more complex versions. I mean, I realize your examples are simple for a reason, but how do we, there's a real complexity of a very different sort that has to get integrated here. And I just don't know what that pathway looks like.
Yeah, so that's a great question. And this is something that troubles me as well. So let me answer, and then maybe somebody else, another machine learning person who's here may be able to answer. And I will reflect my own bias, which is, if you look at people if you look at the research in machine learning, there's some people who are really interested in pursuing what I would call artificial general intelligence, trying to see what an AI can learn strictly from data. And I think at least some of the taste of what I described here reflects that we're trying to, we've got an objective that somebody, there is the dirty little secret, somebody has to write the original reward function, and but even and somebody has to decide what the representation of state is, even or if it's from pixels or images, whether it should be images but an image of what and how much needs to be included. There are decisions that humans are making, but my personal view is that even a human being that is learning from birth to adulthood, till death, learns from many different modalities. One would never expect, I don't know that we expect our AIs to go from, to relearn calculus and physics en route to learning how to master some particular problem. And so for me, I sort of feel like we should provide some of the benefit of the things that our society has already agreed upon, and encode them and experiment with them and see, how those systems work using both those modalities and experience and experiment from this sort of trial and error type of learning that we do with reinforcement learning. But many people will disagree with that, and they will say that you know, and it could be that it doesn't work. Many people will say that you need to learn those rules, that those rules will emerge from the interactions of these agents in these societies, that better rules will emerge. But there's a disconnect between that sort of long-term view of how intelligence is going to emerge and the study of it and using these systems as sort of Drosophila for us to study and understand intelligence, versus this notion of actually going out and building a system in the next 20 years that's going to actually do something and that we actually trust sufficiently to go out and operate in the world and that we feel comfortable with. But you know, I'm guessing that Brian has an opinion on this. I'm guessing that some of the machine learning people who are here may have an opinion and a differing opinion on that. So I would welcome somebody else to answer that in a different way if they like. Now or later, yeah.
we'll keep it open, and yeah. We'll get to Brian in a minute, but first to Jonas.
Hi, thanks for the wonderful presentation. I really enjoyed this. I guess this is related to the answer you just provided, so maybe we can further that discussion a little bit. So I know you mentioned that a key challenge for the field is gaining an accurate distribution over the value functions of the other agents. And this certainly seems like a very essential component for deploying a framework like this in practice. So I was wondering if you could share some insights on how you currently think we can potentially get this distribution, right? So like, do you see this as, like you mentioned, being learned through interaction with other agents and potentially arising via emergent behavior, or should we define this distribution over value functions that, you know, we as humans think seem fair? And I guess this would be more closely aligned with what you just mentioned with the different modalities of learning and providing the agents with some sort of encoded rules of society. Or perhaps should the agents explicitly share their value functions with each other? How do you think this process would look like?
Yeah, so well, I have no one fixed answer. It is a problem. I can imagine them emerging through experimentation in an environment with a distribution of tasks that need to be performed. So you can imagine for any particular environment, you can imagine a distribution of tasks that you might want to perform in that environment, and generating, you know, the value functions that way. One could imagine, you know, encoding or programming a generative model that might give rise to these value functions as well. A third way, and I think that was one of the reasons why we found this options framework a nice middle ground, and perhaps a more tractable middle ground, in the sense that the options provide a sort of a pre-articulation of things, and maybe those options were learned, but they provide a pre-articulation of things that you know, skills that you know you want, a subset of states that are the initiation states that you can focus on as being, and either test whether whether they're reachable or not reachable, or you know what value you get from that option starting in one of those initiation states. And so those are just some examples, but yeah, or you know, going back up the ladder and encoding it. But here we were looking, and there may be radically different ways of doing this. And sort of back to Reed's question, we may just want to, you know, simulate it all as we go along. That we've just got these, that we create this recursive set of you know, I'm thinking about, you know, I'm the acting agent and I'm thinking about you, and now I go inside your mind, like theory of mind, and simulate what's going to happen and find some optimal policy for you under this, and then it goes back and forth. There are many different ways in which you could imagine sort of making it work.
Thank you.
So hard question, hard problem, or yeah, no perfect answer.
Great, thanks. Brian.
Yeah, thanks, Sheila. So my question has to do with in psychology, with the emergence of behaviorism and then the fall of behaviorism. You know, Chomsky's response to Skinner and Fodor and others in philosophy of mind. It was kind of recognized that you can't know how to behave or figure out how other people will behave purely in terms of behavior. You have to actually think in terms of what people know. And so model what people know, not just their behavioral repertoire. And the thing about knowledge is that, I mean, there are a lot of things about knowledge. It's not sequential. In order to understand what someone knows, you have to actually model the compositional structure of that. I mean, because all the structure of logic sort of emerges when you're actually modeling a mind. And you just mentioned theory of mind yourself. My concern is that the value functions and the options and stuff are still, now maybe I'm wrong, but I feel as if there's still a sort of sense that you can get at what's going on in terms of behavior. Now, of course, it's a long way from there to a theory that actually models the theory of mind of all the other agents in the system and stuff. But I'm just curious what the transition looks like. First of all, how do you deal with knowledge, what the other agents know as opposed to what they do or will do? And then what is the transition from where you are now to that full, much more tough problem? What does that continuum looks like? Do you think there's any coherence to it, or is it a big step function?
Yeah, that's a great question. And I'm sure I see my Anshvo here, who's a senior graduate student or my senior graduate student who has, dedicated his PhD thesis to looking at precisely some of those questions, theory of mind, how one builds a theory of mind for a variety of tasks, including explanation and goal recognition and using logic, but using logic and using models. And there is work in, deep theory of mind or machine theory of mind. There is some work that is trying to do some of these notions of being able to model the other agents. But, we are so far from that right now with reinforcement learning. Even partial observability is a challenge. Partial observability and understanding what to remember, what you need to remember and what you need to forget, or what you can forget. Just going from one state to the next is something that eludes most of these systems. But I mentioned it because I agree with you. I think that in the long run, what we really, this is like tic-tac-toe. We're these are baby steps, but they're baby steps that I think open the door, at least to ask the question and open the door to people in machine learning starting to think about things that I think people in psychology and in philosophy and in knowledge representation and reasoning have been thinking about for a long time, but thinking about once they have models. I'm sort of hoping, like, to answer your question in a different way, I'm sort of hoping, this deep learning and machine learning is so powerful because of its ability to deal with perception and to ground thinking in perception. I'm sort of hoping, and now we see even in reinforcement learning the appreciation for models and for model, but learning a model as well as just learning a policy. I'm hoping that all this work doesn't have to go down, but that people will, as we solve some of these problems, will regain an appreciation for using models, and we'll go back to using these models, and there will be an easy pathway. That's what I'm betting my path on, and I've got that particular issue on my mind, as does Mayan. I think this notion of how we can do these, much more sophisticated lines of reasoning, which I think are so essential and so fundamental to us as human beings. Yeah.
Well, thanks. I'll drink to that.
Yeah,
I hope we will be soon. Allison.
Hello. Thank you, Sheila. That was really awesome to be able to think about ethics and reinforcement learning for a moment. It's been a while since I've taken an ethics class, but which is kind of like leading me into this question of like whenever we're talking about reward functions, I think utilitarianism, and I think that I wonder if reinforcement learning is limited because it has all the problems that utilitarianism has by trying to cram everything into like this idea of value, of happiness. I don't know very much about utilitarianism. That's kind of like the limit of it. But I wonder, like, in your opinion, this research, like, are there parts of it that are like inherently limited by as like a moral theory, I guess, or a moral tool, because we're using the reward function and value function? Like, if you were to hand this to an ethics student or an ethics professor, like, how would you go about it, having that conversation with them? Like, here's a tool, or here's a toy. Like, how would you present it to them?
Yeah, so you know, it's above my, it's a great question, and I almost feel like so some of those people that you are that you're concerned about are actually here right now, and maybe I don't know whether it's a cop out to punt and ask one of them to answer that question. I think, I don't know, Jennifer, I don't know whether you can sorry to put you on the spot, and so you can decline, but can you answer Allison's question?
I'm not an ethicist, but I don't think you're constrained to utilitarian moral frameworks by your formal apparatus, because agents could value anything. They could value the, continued survival of the species. That, it's, and I think the sort of summative character of utilitarianism doesn't have to tie your hands in the kind of modeling that you're doing. I do think there are maybe some moral theories for which your model as it stands doesn't capture what's going on. You would have to put constraints on the kind of value functions that the agents could have, but it's not necessarily utilitarian given just what you have so far.
Thank you. Allison, does that answer your question, or does that help?
Yeah, what are those moral theories that aren't covered by this approach then, Jennifer?
Well, I think it's really quite underspecified. So there's just sort of there's no very quick answer to the issue that you're raising. It's going to depend a lot how you specify the the content of those value functions. It's really pretty abstract so far in the model that Sheila's providing.
Yeah, then I guess my next question would be, how would you even begin to do that? Like, how would you recommend, like, taking this formulation, trying out a different value function, comparing it to a moral theory, like mapping the two, or trying to show what this covers?
For one thing, you might have to enrich the model in various ways. Like, you might have to make it the case that agents aren't fixed in terms of what they value, but they can learn to value different things through processes of social learning, where they're coming to make better and better judgments about what has value, where their judgments are informed by their interactions with other agents, for example. So you could kind of like enrich the model in some direction like that. But there's a lot of different ways you could go with this.
Yeah. I wonder if I could jump in here, because I think, and I'm going to echo Lisa from a little earlier, not surprisingly, perhaps. So if we think about where you started, Sheila, which was the problem of, the specifying all the rules and norms of, how you should behave, and the challenge of that specification. I guess I'm wondering if you're solving that in the sense that, these questions about, like, what should your coefficients be? What values should you be using? Even a more elaborate model than that. I'll say the reason I actually started talking to my son about computer science and eventually found my way to this area was thinking about theories of law and the computational problem that you face when, as a single agent, you kind of have to track all of these things about how is everybody else behaving, what do we all think is okay, because I think ultimately those, in your model, the alphas are socially determined. that is to say, what does it mean to be considerate is something that is socially determined, and through lots of different mechanisms, both formal and informal, that we come up with that, which kind of always gets me focused on thinking about, okay, so how are we going to build our machines to hook into the processes, the formal and informal processes by which we decide things, like was it considerate or not inconsiderate to leave the key in room 2 rather than in the common area. I mean, that's the stuff of, you know, our constant conversation. And then, as Lisa points out, eventually we get to, or you probably can't bring an action in court for not leaving it in the common room, but you could perhaps for trampling through somebody's garden. I guess anyway, so I think that's really just an observation. I'm totally on board with, we need to build simple models to try and explore these concepts, and just kind of wondering, you know, if this is the solution to the problem of specification, or it's a path to one, I guess is it powerful enough? There is something, we can't say meta anymore, but anyway, of the idea that it's, rather than knowing specifically what you should do, it's like, okay, here's a concept. Don't make the world worse for other people. As I guess Jennifer said, that's right. They keep, like, you know, but sometimes those other people, they don't have legitimate expectations, or they don't have, they have wicked values or something.
Yeah. So I think I think that it's a great discussion. I don't have the wisdom to have the answers, but I certainly think that some combination of you know, again, an articulation of some social norms or expectations for behavior within an environment, and as we have done in, you know, when we do knowledge representation and we talk about defeasible, well, this applies unless this, you know, here's the default unless this occurs, and that we can create some sort of a mechanism for that, together with learning about what's experimenting in an environment. So we can use those as either, you know, I would call them pruning or filtering, as Jennifer called them, to sort of further constrain what's defined as allowable behavior, and then to search for optimal policies within that further constrained space. So now everything goes, and you're just maximizing your reward, but maybe we want to constrain what's actually permissible in these environments, or socially permissible, or whatever words you use. Those words all, they don't scare me, but they're loaded, and I know they're loaded for different people in different ways. So I'm always hesitant to use them, but something that will further constrain the set of policies or behaviors that we may want to allow. But again, to Brian's point, you know, behavior is not, you know, that's already been played with and rejected. We've gone beyond that. So, but it's a start.
Yeah. Thanks, Sheila. Brian, one last quick word.
Yeah. So just on Allison's question, I was just going to say that, you know, I feel as deeply as anyone. I think that a lot of AI models are very limited. I'm not myself a fan of putting too much weight on the notion of reward and all of this kind of stuff. But nevertheless, my experience has always been that the ways in which AI models are limited doesn't map simply onto the conceptual distinctions that have been made in philosophical discussions. I mean, it's one of the reasons why I think these SRI discussions are so important, because you know, things can look as if they're utilitarian or materialistic or this or that and stuff. You know, I have some sympathy for Nussbaum, like, you know, you know, theories of ethical qualities rather than consequences of behavior and so on and so forth. But I think that the joints of the territory that we're exploring with these AI models, and the joints of the territory, the way philosophers have theorized ethics, don't match up in any simple way at all. And one of the wonderful things that I look forward to with the SRI and the graduate students coming up is some real sophistication with respect to how the fine structure of these different fields relates to each other. I don't think we're going to find simple ways of getting the categories of one mapped across onto the categories of another. I think it's going to be very fine textured and layered and nuanced, and there's going to be wonderful dissertations coming out, and I will die off long before this territory is understood.
Well, stick with us, Brian. Yes, nuanced, layered, wonderful. Sheila, thank you for a really wonderful talk. So really thought-provoking. I know we'll continue those conversations. Jack has popped a survey into the chat if anybody has a moment to share some thoughts with us. And next week, we're looking forward to hearing from, it's our last seminar of the term, Rosalie Wang, who is a faculty fellow with us at Schwartz Reisman, an assistant professor in occupational science and occupational therapy here at U of T. And her talk is on the future of everyday lives, older adults, caregivers, and AI-enabled health and social care. And we look forward to seeing you next week. Thanks again. Take care, everyone.
Thank you, everyone.